Steinhauer here. Welcome back. Still talking about general relativity with Einstein and how that can now relate to black holes. So let's recall what we were talking about when we took this aside to talk about relativity. We were talking about large, massive stars that collapse at the end of their lives, and how very large stars go supernova, and that core collapses into a neutron star, and that neutron star is supported by neutron degeneracy. Well, if that collapsed core is big enough, then not even neutron degeneracy can support that core. In fact, if the mass of the core of that star is more than 3 times the mass of the sun, then neutron degeneracy cannot support it anymore. And once neutron degeneracy cannot support the star anymore, we know of no known forces that can support this star. There's nothing that we know of that can support this object against collapsing in on itself. So what does that mean? It means it collapses down into nothing. It collapses down into an object with 0 radius. We call such a thing a singularity. So what is the escape velocity from the surface of a singularity? Let me remind you what the escape velocity formula is. Escape velocity squared is 2gm divided by r, right? If you make r and make it go to 0, as r goes to 0, the escape velocity goes to infinity, right? If you make an object whose radius is physically 0, the escape velocity from the surface of that object will be infinite. Well, that's interesting. Obviously, singularities are a problem in mathematical situations because you end up dividing by 0, which is why there's a problem. So let's ask a different question. What is the radius around this singularity where an object's escape velocity goes to the speed of light? Remember, the further away you get from that object, the lower the escape velocity gets. So what is the relationship between radius and mass when the escape velocity equals the speed of light? Well, we can use our equation from the previous, or escape velocity equation. We can say V escape squared equals 2 times g times m divided by r. Well, where are you when the escape velocity equals the speed of light? All you need to do is plug in the speed of light for the escape velocity. C squared, the speed of light squared, is 2 times g times m divided by r. This is the case where you are, where the escape velocity is equal to the speed of light. Let's solve this for r now. Multiply both sides by r. You can divide both sides by c squared. The c squareds cancel on the left, the r's cancel on the right, and we're left with this equation. R equals 2 times g times m divided by c squared. And this radius, we give a special name to. We call it the Schwarzschild radius. Let's give it a little RS. And it's named after Schwarzschild, who's spelled his name this way. Schwarz's child. Oops, I forgot the L there. The Schwarzschild radius. So this is how far away from an object, which may be a singularity at the center, you have to get before the escape velocity becomes the speed of light. And so this is an important region because nothing can move faster than the speed of light. So if you get within an object's Schwarzschild radius, then nothing can escape it. Not even things moving at the speed of light. Not even light. So what is a black hole? A black hole is an object whose physical radius is smaller than its Schwarzschild radius. Because if you have an object whose physical radius is smaller than its Schwarzschild radius, then any light even that's emitted from inside that radius or from the surface of that object cannot actually escape at all. That's a black hole. All light, no light can come from the black hole. All light gets that comes by, that enters the black hole's Schwarzschild radius cannot escape either. Here are some examples of objects and how light escapes from the surface of those objects. In the upper left, we have a normal star undergoing fusion. The surface gravity is weak enough on the surface of a normal star like the sun that light can escape without experiencing really any problems at all, or any curvature that's measurable on the scale. White dwarfs, again, you've taken all of that mass and made it into a much smaller object, something the size of the Earth. Now you see you have small effects where light is bent a little bit as you exit the surface of a white dwarf. A neutron star is pretty close to its Schwarzschild radius. It's not quite there, but it's pretty close. And you can see some light that leaves the neutron star might not even escape, but some light will be able to escape. If you get a light beam moving straight enough up, that light beam can escape the neutron star's gravitational field. A black hole, again, there may be some physical force that can support this object inside here. It may be collapsing down to zero. It may not be collapsing down to zero, but it doesn't really matter. Any light that's emitted from the surface of that, whether it's at the very center or not at the very center, none of that light will escape. It will, in fact, enter orbit or get trapped and never leave the Schwarzschild radius area. And so that's why they're called black holes. No light can escape from the surface of these objects. So let's do we have an equation, we can do a calculation. What is the Schwarzschild radius of a black hole that has a mass of 10 solar masses? Let's do the calculation. We know that the Schwarzschild radius is 2 times g times m divided by c squared. We know that the mass is 10 solar masses, and we know that one solar mass, that's 10 times one solar mass, which is 2 times 10 to the 30th kilograms. 10 times 2 times 10 to the 30th is 2 times 10 to the 31 kilograms. What is c? C, the speed of light, is 3 times 10 to the 8 meters per second. C squared, you square the base and double the exponent, is 9 times 10 to the 16 meters squared per second squared. And we know that g is, we can plug these numbers in. The Schwarzschild radius should be 2 times g, which is 6.67 times 10 to the negative 11. Oops, that was too many ones. 10 to the negative 11 meters cubed per kilogram times second squared. We know the mass is 2 times 10 to the 31 kilograms. We're going to divide by c squared, which is 9 times 10 to the 16 meters squared per second squared. When you plug all that into a calculator, you get 29644. And what are the units on that number? Well, kilograms here cancels kilograms there. We've got second squared canceling second squared there. We've got meters squared canceling 2 of the 3 meters squared up there. And the only thing that's left is 1 of these meters. And so this is almost 30,000 meters, or about 30 kilometers. The Schwarzschild radius of a 10 solar mass object is 30 kilometers. This is a pretty small distance for 10 solar masses to be compacted down into, obviously. Now, this leads to a very much simplified version of this formula. I want you to see what we did here. All of this stuff here, let's go back to our original Schwarzschild radius equation. All of this stuff here in our original Schwarzschild radius equation are constants. The 2 and the g and the c squared, right? So the Schwarzschild radius is proportional to mass. What is that proportionality constant? Well, basically it's 3, right? If we plug in 10 solar masses, we get RS in kilometers multiplied by 3. So this leads to a much simpler version of this formula if you're dealing with solar masses in kilometers, right? So RS, I'm going to call this RS prime, and I'm going to label it blue so you see the difference, is just equal to 3m prime, right? Both of these equations are right, this one and this one. This one down here is much simpler, but you have to remember that in order to use this one, you have to plug in mass in solar masses and radius in kilometers. In other words, you plug in a mass in solar masses, you get a radius in kilometers, or vice versa, you plug in a radius in kilometers and you get a mass out in solar masses. This is the formula that you need to use if you have things other than kilometers and solar masses. But here you have to use the units of G, which have meters and kilograms and seconds. So if you plug in meters, and the mass here has to be in kilograms, and you'll get a Schwarzschild radius out in meters. Both of these equations are right. You just have to use them with the right units. Okay, so let's try this equation out. How massive is a black hole whose Schwarzschild radius is 600 kilometers? Why don't you go ahead and try this one on your own, and then I'll come back and we can do it together. Okay, let's use the simpler formula. We know that RS prime equals 3m prime. We're given a radius in kilometers, right? So we can just plug this in. 600. Again, I don't need to know about the units because I know if I plug in kilometers, I get out solar masses. Equals 3m. Divide both sides by 3. The 3's cancel out over here. I get m prime equals 600 divided by 3, which is 200. And what are the units? We know in this particular case, it has to be solar masses. So this object, which has a Schwarzschild radius of 600 kilometers, must have a mass 200 times that of the sun. Okay, so we've been talking about the Schwarzschild radius. This is what we can consider the surface of a black hole, right? This is the defining layer of the black hole beyond which you cannot escape, beyond which no information is available to you. And so the surface of a black hole is defined to be the Schwarzschild radius. We also denote this and call it sometimes the event horizon, right? The event horizon and the Schwarzschild radius are basically the same thing. Why do we call it the event horizon? Because since light can't escape from inside that radius, we can know nothing about what's going on from inside that radius. It's not just light that can't escape, nothing can escape. No information can be transferred from inside that black hole to outside that black hole. It really is an event horizon. Anything that happens within that will never be seen or known by anybody outside that radius. It is a real event horizon in that sense. How big is this? Again, this is pretty similar in size to a neutron star. A neutron star is almost a black hole. The event horizon of a 3 solar mass black hole is about 9 kilometers. Remember, we were talking about the size of a neutron star being 10 kilometers or so. They're slightly less massive, obviously, than three solar masses, but a neutron star is already pretty close to its Schwarzschild radius. It's pretty close to being a black hole already. Okay, here's a survey question for you that you may or may not know the answer to, but I want you to think about it. So here's the question. What would happen to the Earth if the sun were suddenly replaced by a black hole that had exactly the same mass as the sun? Do you think it would be sucked into the black hole? Do you think it would become unbound and fly off into space? Do you think the Earth would remain in the orbit around the black hole, but with a much shorter period? Or do you think it would remain in orbit around the black hole with the same period as it has now? Go ahead and make a guess, and we'll talk about what the answer is. Okay. This is highlighting one of the most common misconceptions about black holes, and that is that they suck in everything around them. But if you don't remember anything else about black holes, remember this. Black holes don't suck. This is important. They are massive objects the same way that anything else is a massive object. Let's try to visualize this. Okay, so here we have an object, and this is, say, the sun. It's got a fairly large radius as radii go of things that we're talking about, and it's got a reasonable mass. And we're looking at this in the same way we looked at it before, thinking about space-time as a curved object. And we're thinking about a two-dimensional view of the space-time around this massive object, because it's impossible to visualize this stuff in 3 dimensions. So this is equivalent to the toy at the Science Center that we talked about in the previous video. Put the quarter in, it orbits around and eventually falls in. The Earth is exactly like one of those coins, except there's no friction, and so it doesn't spiral in, and so it just remains in orbit around this thing. Okay, so what's going to happen if I make this object less massive? I'm going to move this slider bar to the left. What do you think is going to happen to the curvature out here if I make this object less massive? What's your prediction? Say it out loud, write it down. All right, let's actually move the slider bar and see what happens. Oh, it becomes less curved, which isn't terribly surprising, right? The more massive you make an object, the more it curves space-time in the region around it, and therefore the higher force of gravity is felt by things that are right around these things. Make this thing too massive, it becomes a black hole, and it's lost. You have an event horizon then that grows from there. But let's just think about our star again, and thinking about, so decreasing the mass decreases the curvature in a particular radius, and increasing the mass increases the curvature at a particular radius. What's going to happen if I move the object radius bar? Let's say I'm going to make this object bigger or smaller without changing the mass. How do you think that's going to affect the curvature out here? Let's do it. Making the object bigger, making the object smaller. How is that affecting the curvature in the space-time out there? It's not, right? An object that's orbiting out here has no idea, really. It doesn't care how big this thing is that it's orbiting. It doesn't change the curvature of the space-time at this distance from the center of that object. All that you do by making this thing smaller, is you make more space available. You can get closer to the center of it, and so space-time is curved in this region right around it more than it was before. But this space didn't even exist. It was inside the physical object before. It just allows you to get closer to the center of that object and experience higher space-time, higher curvature of space-time, until it's curved too much and it just goes to be a black hole, right? But for the purposes of our question, which was what happens to our planet out here, if it were replaced with an object that had exactly the same mass as the sun, the curvature out here is not affected at all by what the radius of this object is at the center. The Earth would be unaffected. It would still orbit in a perfectly happy 1 year period, going around the black hole as normal. It would not be sucked in. Black holes don't suck. They're just massive objects in space. Right, now other bad things would happen to the Earth, right? It's sitting here at the Earth, if the sun goes away and is replaced by a black hole, obviously life dies out fairly quickly because there's no energy reaching us anymore and bad things happen. But the orbit is actually unaffected. Okay, we've already talked about this a little bit, but inside the black hole, there are some interesting things going on, right? We have no escape possible from the center of a black hole. Nothing can escape from within the event horizon because nothing can go faster than the speed of light. And in fact, there's only 3 things that you can measure about a mass. You can measure about a black hole. You can measure its mass, you can measure its spin rate, and you can measure its charge. Everything else is completely destroyed inside a black hole, meaning we can't know what it's composed of. We can't know if there's protons. We can't know anything about what's inside that black hole. We can't know what color it is. No information can leave from inside that black hole other than the total mass, the total spin, how fast it's spinning, and the total charge inside that. And those are only by effects that are measurable outside the surface of the black hole itself. Okay, we'll come back in the next class and talk more about black holes and more about the crazy and interesting things that happen when you get close to black holes. I'll see you then.